It was just an accident, a seemingly minor accident, but it might have become a tragedy were it not for mathematicians and a miraculous X-ray machine called a CAT scanner. Images of the human body are not a recent phenomenon. For hundreds of years, artists and scientists like Leonardo da Vinci and Andreas Vesalius have carefully detailed the insides of the human body, providing physicians with a valuable, though limited, medical tool. Then, with this strange-looking machine, medical imaging took a giant leap forward. In 1895, physicist Wilhelm Roentgen accidentally discovered that certain rays, he called them X-rays for unknown rays, could pass through solid substances. With this device, Roentgen was able to see what was inside the body. It was a discovery that earned him the first Nobel Prize in physics. Early in the 20th century, Thomas Alva Edison, the inventor of the electric light bulb, tried to improve upon the primitive equipment used for X-rays, but failed. And though X-ray photos were enhanced over the years, there was still a problem. Robert Ledley, a pioneer in medical imaging and professor of biophysics and radiology at Georgetown University Hospital, explains.
One of the initial problems was that the X-ray basically saw bones more than anything else, and they had to think of ways of seeing other things. And one of the methods was to use contrast media, that is, to inject into the arteries of the patient some kind of substance which would be radiopaque and stop the X-rays so that the blood vessels could be seen. But basically, to see muscle was very difficult, and to see individual organs, it was very hard. And especially, of course, in the head, the skull blocked out a lot, and even though you could get X-rays through the skull, so still it was very hard to see things inside the skull.
Can you open your eyes as wide as you can?
But for our young bicyclist, that's exactly what was needed. Doctors called for a traditional X-ray, which showed a light skull fracture, but nothing more. Nothing of the unknown danger that lay hidden inside the skull. Interestingly enough, way back in 1917, Johann Radon, a mathematician from a province in Czechoslovakia, had worked on a method for finding an unknown value at a point inside of an object. While having some fun with mathematics, Radon proved that it was possible to reconstruct the numerical value at a point in a region if you knew the sum of the numbers at the points that lie along a number of lines that pass through that region. Without realizing it, Radon had laid the mathematical foundation for the creation of a device that would accurately and clearly see inside the human body. But it wasn't until 1971 that there was a major breakthrough in X-ray technology. Physicist Godfrey Hounsfield invented a computer-assisted X-ray machine that could take a photograph along an XY plane inside of the brain. This photographic slice of the brain was called a tomograph. And for his computerized axial tomographic scanner, CAT scanner for short, Hounsfield was awarded the Nobel Prize. How does the CAT scanner actually help us find an unknown number, or density, inside the body, inside the brain? At AT&T Bell Laboratories in New Jersey, Larry Shepp, a mathematician who has worked extensively with the mathematics of CAT scanning, explains the process.
The way that the CAT scanner works, let's illustrate it on the head. Think about one plane through the head, and think about an X-ray beam along one line in that plane. And it goes through here, and there's a detector on the other side that measures what fraction of the X-rays actually get through. If I know that fraction, then I can find out the sum of the densities along that line, the so-called line sum or line integral.
The modern CAT scanner sends thousands of such X-ray lines on a selected XY plane as it rotates around the body. Using techniques involving logarithms to calculate the sum of the densities along these lines, the CAT scanner can construct an X-ray photograph of those densities. It is the practical application of the theoretical problem Radon solved earlier in the century. Larry Shepp.
The CAT scanner can be demonstrated on a very simple model. Suppose we had an object that was made up of 3 different densities, A, B, C. Actually, when we're talking about a head, or a body part, it will have many, many different parts. But let's say we only had 3. And suppose that we passed, X-rays along this line here. Now, I can get A plus B. And if I take the line along here, I can get A plus C. And if I take the line along here, I can get B plus C. And now, in Radon's situation, he would have A plus B is equal to X, and he would have A plus C is equal to Y, and he would have B plus C is equal to Z. And he would say, how would I solve these equations? And he would say, well, in this particular case, I would solve them as follows. I could say that X minus Y is equal to B minus C. And since Z is equal to B plus C, if I add these equations, I get X minus Y plus Z is equal to 2B, and therefore B is equal to X minus Y plus Z times a half. And similarly, I could solve for A and C. This is a very simple model where you can solve the equations to determine the unknown density values. I happened to be in Columbia Presbyterian Hospital in New York City on the day when Godfrey Hounsfield in England, of England, made his first presentation in the United States of the CAT scanner. And I asked him, was he using Radon's formula? And he said, no, he didn't know about Radon's formula, and he did it by an iterative method. Let's see how Hounsfield would attack this problem. What he would say is, well, suppose I measure that A plus B is equal to 6, and A plus C is equal to 9, and B plus C is equal to 11. He would begin, his method begins with an initial guess, say an initial guess at A. Suppose that A is 1. In that case, since A plus B is 6, we find that B is 5. Since A plus C is 9, we find that C is 8. But then 5 plus 8 is 13 is too big. Well, he might say, well, suppose A we guessed was 3. Well, then we would have 3 plus B is 6, so B is 3. And C then would be 6. But then 3 plus 6 would be 9, and it's too small. In that way, eventually we might then guess that A equals 2 is the right start, and then we would get into a loop, which would then be right. If we started with A equals 2, then we get 2 plus 4 is 6, so B is 4. 2 plus 7 is 9, so C is 7. And now 4 plus 7 is indeed equal to 11, and it's right. And that's the way Hounsfield's iterative procedure would work.
The key idea, which pioneers like Radon and Hounsfield understood, was that if you knew enough line sum equations in enough directions, you could find each unknown value.
Now, Hounsfield did it on the basis of his intuition. Radon did it on the basis of a mathematical theorem or a proof, but they both came to the same conclusion with different methodology or different algorithms. The word algorithm is what really is used now to describe the procedure by which the measured values are turned into the actual density so that we can look inside the head.
But how do we turn these numbers into pictures?
What you do is make a grid, which is an array of little picture elements or pixels. the Radon procedure would give you the density values in each of these little squares. Well, what you do is you make a gray level correspondence, a gray level code. In Hounsfield units, 2,000 is bone, 1,000 is water, 0 is air, and 1,050 would be blood, and 1,030 would be tumor, say, and 1,020 might be gray matter. And when you do that, you get an image.
Building on Hounsfield's basic concepts and encouraged by Georgetown University, Robert Ledley invented the first full-body scanner, the ACTA scanner. It came not a moment too soon.
One of the first patients that we had was a little boy who had fallen off his bicycle. At least that's what the little boy had said, a 4-year-old boy, because the parents didn't see it. And he came in and said he hurt his head, but the parents didn't see him fall off, so they had to take his word for it. And then he acted a little drowsy. So they took him down to Georgetown, and it turned out that was a Saturday, and Dr. McCulloch, who was a pediatric neurosurgeon, happened to be there. Dr. McCulloch looked at the child, and sure enough, he was sort of drowsy. And normally, they would have put him in the hospital and just observed him overnight. But Dr. McCulloch also had been watching from time to time the use of the scanner, and being a really brilliant man, he said, why don't we scan the child in the CT scanner and see whether there is a hematoma or some problem in the brain. So he went upstairs, and just from watching people, he knew how to use the machine. And he ran the machine himself, because I wasn't there, the technicians weren't there. He scanned the boy's head and the child's head, and sure enough, there was a hematoma. There was blood in the child's brain, which was getting, pressing on the brain, getting worse and worse. And he immediately took the child to surgery and took out the blood. And the boy recovered very nicely and was perfectly normal. And Dr. McCulloch told me, he says, there isn't any question that that boy would have died overnight hadn't we had that scanner.
Mathematicians have already found a way to enhance basic CAT scan technology in order to create 3D reconstructions. But what of the future? What role will mathematics play?
Well, it's hard to predict the future, but it's very clear that in, for example, PET imaging, positron emission tomography, it will play the role of being able to give us some insight into the function of the brain, where the processes take place. For example, which part of the brain is active during mathematical thinking? Where do we do our addition and subtraction? Is it in the same place? And how are these things processed? And in order to do that in the best way, mathematics again will be playing the central role as it does in tomography itself.